Now that you've been through part A of this lecture number 7, and presumably you've come to terms with the big O notation, you got a pretty good idea of why bubble sort in particular takes an amount of time that is big O n squared, and also have a sense that that's true for selection sort and insertion sort. We want to proceed to a harder complexity analysis, time complexity analysis problem, specifically merge sort. Nevertheless, the question is an important question, and while it can't be answered with a precise answer, a definite numeric answer, we can talk about how long it takes bubble sort to sort in a way that is, well, not complete in a sense. Still, we can give an answer that is meaningful and mathematically rigorous as well. All right, before we look at the sorting algorithms that we've been discussing and develop a rigorous way of analyzing them, let's start with a more basic, a simpler bit of code. So here's something that you may have done in your introductory programming course. You may have done exactly this or something quite like this. Let's look at this code. So this code basically has a nesting of two loops. The outer loop loops n times. I'm assuming some value for n is specified beforehand. So the outer loop loops n times, and the inner loop also loops n times. Every time through the inner loop, let's assume that a single asterisk is printed. So of course, in the Java world, that would be system.out.print, parentheses, double quotes, asterisk, double quotes, parenthesis, semicolon. And for C++, it would be cout less than, double quotes, asterisk, double quotes, semicolon. Okay, but anyway. And then after the inner loop, let's assume that a carriage return is printed. Okay, so as I say, you've probably done this sort of thing. This is important for computer scientists and for software developers. It really is important to be able to analyze algorithms, not just acquire, a large, not to just amass, a big collection of algorithms to do things. Okay, here's a question. How long does it take to sort an array of size n using bubble sort? All right, the answer is there is no answer. This question is not well stated because algorithms by themselves don't take any amount of time. What actually takes time is a computer program, and the amount of time that a computer program takes to execute depends on a lot of details, including the speed of the central processing unit in the computer, various hardware aspects as well as software aspects. How was the code written? How was it compiled, and so forth. Nevertheless, the question is an important question, and while it can't be answered with a precise answer, a definite numeric answer, we can talk about how long it takes bubble sort to sort in a way that is, well, not complete in a sense, still we can give an answer that is meaningful and mathematically rigorous as well. All right, before we look at the sorting algorithms that we've been discussing and develop a rigorous way of analyzing them, let's start with a more basic, a simpler bit of code. So here's something that you may have done in your introductory programming course. You may have done exactly this or something quite like this. Let's look at this code. So this code basically has a nesting of two loops. The outer loop loops n times. I'm assuming some value for n is specified beforehand. So the outer loop loops n times, and the inner loop also loops n times. Every time through the inner loop, let's assume that a single asterisk is printed. So of course, in the Java world, that would be system.out.print, parentheses, double quotes, asterisk, double quotes, parenthesis, semicolon. And for C++, it would be cout less than, double quotes, asterisk, double quotes, semicolon. Okay, but anyway. And then after the inner loop, let me give away the punchline here. Here's what our plan is. We're going to establish, pretty much prove with pretty much rigor, the fact that the amount of time required to sort an array of size n using Mergesort is big O n base 2 log of n. Okay, so that's big O of n multiplied by the base 2 logarithm of n. In order to come to understand this, we need to think about the recursion involved in Mergesort again, and particularly again the levels of recursion. We talked about this and had a figure when I introduced Mergesort. We're going to see basically the same figure on the next slide. Okay, so here we go. When Mergesort is called the first time to sort the entire array, we refer to that as the level 0 call of Mergesort. Okay? And then there are a couple recursive calls, right? The level 0 call involves splitting the original array into two halves and making recursive calls on each of those halves. We refer to those two calls as the level 1 calls. Okay? Then each of the level 1 calls results in two level 2 calls. All right? So there are going to be 4 level 2 calls. And each of those results in a level 3 call, and so on, right? So, I mean, assuming n is big enough, then the 4 level 2 calls will result in making 8 level 3 calls, and those will in turn result in making 16 level 4 calls, and so on. Okay? In general, there are 2 to the j level j calls where j will be 0, 1, 2, etc. Until we get to the final level. The level 0 call is responsible for sorting all of the entries in the array. Each level 1 call is only responsible for sorting half as many. So 1/2 of 2 to the k is the same thing as 2 to the k minus 1. I want you to check that carefully and make sure you understand it, right? If n is equal to 2 to the k, n is equal to 2 to the k, so 1/2 of n, that's 1/2 of 2 to the k, that's the same thing as 2 to the k minus 1. Okay? Then each level 2 call is responsible for sorting half as many of those, half of that, right? So half of 2 to the k minus 1 is 2 to the k minus 2, and so forth. Okay, at the bottom level, level k, that will be the final level in this game. Each level k call is responsible for sorting 2 to the k minus k, which is the same as 2 to the 0, which just is a single one entry. Okay? So there are no level k plus 1 recursive calls because level k is the base case. When we get to level k, we're only talking about sorting a single number. All right. Here is the figure that I mentioned a couple slides back and incorrectly said was coming up on the next slide. Here it is now. So this figure is intended to help you think about the recursion involved. So once again, at level 0, we have the original call. At level 1, we have the 2 recursive calls, each of which is responsible for sorting half of the numbers in the array. Okay, n over 2 numbers. N over 2 is the same thing as 2 to the k minus 1. At level 2, we have 4 recursive calls. Each of those is responsible for sorting n over 4 numbers. N over 4 is the same thing as 2 to the k minus 2. And then at level 3, we've got 8 of those, each responsible for sorting n over 8 numbers, and n over 8 is the same as 2 to the k minus 3. And eventually we get to level k. And way down at level k, we have these recursive calls that are responsible for sorting only one number, so they're trivial base case. Okay, every time a recursive call is made, there's a certain a fixed amount of time involved in making a call. If you studied elsewhere what's entailed when a function calls another function, there's a certain amount of overhead involving system stack and things like this that, well, you don't really need to appreciate that here, but you do have to realize that it takes a constant amount of time just to make that call, right, that function call. So we want to think about that time. We also want to think about the time that's spent merging. Of course, a big part of Mergesort is merging together subarrays into bigger subarrays. But for the moment, I want to ignore that merging time. Okay? So how many calls are there altogether? How many times does Mergesort get called? Well, there's the original call to Mergesort, the level 0 call, and then there are the 2 level 1 calls, and the 4 level 2 calls, and the 8 level 3 calls, etc. And finally, at level k, we have 2 to the k of those calls. Okay? So the total number of times that Mergesort gets called is 1 plus 2 plus 4 plus 8 plus 16 plus ... until you get up to 2 to the k. All right, so what we're doing here is adding a bunch of powers of 2 until we get up to 2 to the k. Okay, similar to the situation in part A, it turns out that there's a formula for adding all those numbers together. And it's a pretty well-known formula. You might have seen it in a math class. Don't worry if you haven't. But it turns out that that adding the numbers from 1, adding powers of 2, beginning at 1 and going up to 2 to the k, that's the same thing as 2 to the k plus 1 minus 1. Okay? If you've seen that before, that's great. If not, let me try to convince you real fast. Well, let me try to give you an example. Suppose k is equal to 3. So then 2 to the k would be equal to 8. Right? So we would be adding the numbers 1 plus 2 plus 4 plus 8. And 1 plus 2 plus 4 plus 8 is equal to 15. Right? Well, this formula in front of us, 2 to the k plus 1 minus 1, when k is 3, that would be 2 to the 4th minus 1. So that, of course, would be 16 minus 1, and that is also 15. So it works in that case. This is also a fact that is, well, it's very close. It's related to binary numbers. Okay, I don't want to digress on that right now, but you may have seen this formula in connection with working with binary numbers. Okay, so let's let capital A be the amount of time that is required just to make a single call to merge sort. And I'm not talking about executing all of merge sort. I'm talking only about the overhead time in making that call and doing the sorts of things that make function calls work. Okay? So since we're making 2 to the k plus 1 minus 1 calls to merge sort, the total amount of time spent doing the calls will be a times 2 to the k plus 1 minus 1. All right? Well, now notice that 2 to the k plus 1, that's the same thing as 2 to the k times 2. 2 to the k is just n. So 2 to the k plus 1 is the same thing as 2n, 2 times n. All right? So we can rewrite this distributing through. We can write this as a multiplied by 2n minus a. Okay? In other words, 2an minus a. Okay, so that right there accounts for the time spent making calls to merge sort. Frankly, that's the easy part. Okay, now we have to reckon with the time spent merging. Okay, most of the action in merge sort is, the time spent merging. Okay, and we want to think about this one level at a time. So let's think first about the merging that takes place at the deepest level of recursion. Let me remind you that level K calls are asked to sort subarrays of size 1. And so that's a trivial problem. They don't do anything. They just return immediately. They return back up to level K minus 1. Okay? Now each of these calls at level K minus 1 is responsible for sorting 2 numbers, right? And okay, and how many of these level K minus 1 calls are there? Well, again, there are 2 to the K minus 1 of them, right? There are 2 to the K minus 1 level K minus 1 calls, each of which is responsible for sorting 2 elements. And, well, if you think about it, how much time does all of that take? How many numbers are going to be examined doing that in the original array, right? I mean, there's going to be examining numbers in the original array and copying things in the correct order into the auxiliary array. Okay? Well, every single number in the entire array is going to be copied into the auxiliary array by exactly one of these 2 to the k minus 1 level k minus 1 calls to merge sort. Okay? So basically everything during k merging, everything in the original array gets copied into the auxiliary array, and that happens exactly once for each element of the array. All right? And then there's the time copying back, right? Remember that what's put into the auxiliary array has to be copied back to the original array. Okay? But again, every element is going to be copied exactly one time from the auxiliary array into the original array, just as every element in the original array is going to get copied one time into the auxiliary array. Okay? So that depends on the number of elements in the array, n. And if you think about it, the total amount of time to do all of that merging at level k minus 1 is going to be a constant times n. It's just a constant times the number of numbers in the array. Okay, so if we call that constant capital B, then what we're including here, and I realize this is the hard part to visualize and to really appreciate, but I'm hoping you're thinking about it and coming to the same conclusion as I am here, which is that the total amount of time doing all of the level k minus 1 merging is going to be a constant b multiplied by n. Okay, again, because every element of the array is involved in exactly one of the level k minus 1 mergings. Okay? But here's the good news. If you can figure that out, the exact same thing can be said of all the level k minus 2 mergings. Every single element in the array gets involved in exactly one of the level k minus 2 mergings. So again, the amount of time spent doing all of the level k minus 2 mergings is b times n. The same is said of level the level k minus 3 mergings, same thing, b times n. And this reasoning goes all the way back up to the top level, all the way up at level 0. The amount of time required to merge at level 0 is again capital B times n. Okay? Well, how many levels of merging were there? There was merging down at level k minus 1, and there's also merging at level k minus 2, k minus 3, and so forth, all the way up to level 0. Well, that's a total of k levels of merging. Okay? So we put all the mergings together, and we conclude that the amount of time spent merging is k multiplied by bn. Okay, we can rewrite that as b times n times k. And of course, k is the base 2 logarithm of n. So the merging time is a constant b multiplied by n log n, base 2 log n. Okay, now we simply add the merging time, bn base 2 log of n, to the amount of time spent making recursive calls, which we decided was 2an minus a, and we come up with a complete accounting of the time spent doing merge sort. Okay? The time spent to merge sort the entire array is going to be 2 times an minus a plus b n log n. All right, now this is kind of the good news about the big O notation. When we look at something like this, what we need to do is realize that n log n multiplied by the base 2 log of n, is eventually going to be much greater than n. Now, a little timeout. It is true the base 2 logarithm of n grows rather slowly, but eventually it's going to be pretty big. When n gets big enough, base 2 logarithm of n is going to be pretty big. Okay? And then n times the base 2 logarithm is going to be much bigger than n. Okay? And if you let n get sufficiently big, then these constants a and b don't even matter. All right? You can say that eventually, once n gets big enough, b multiplied by n base 2 log of n will dominate the other terms. It will be much bigger than the other two terms, right? The 2a and the minus a. Okay, anyway, it's bn log n will eventually be bigger than 2an. Okay, because that term dominates like that, the nice thing about the big O notation is you get to ignore the other terms and just focus on the bn base 2 log n term. And the big O notation allows you to ignore the constant b factor, and you wind up saying that the execution time for merge sort is big O n base 2 log of n. Okay? Yeah, it's a little bit hard to swallow at first, but that's the way it works. Okay? And once again, what does it mean? It means that the amount of time that it takes to execute merge sort is never going to be any worse than some unspecified constant multiplied by n times log to the base 2 of n. All right, we're going to give lip service. Well, we're going to get less involved with quicksort and basically just make some claims here without digging into it too hard. Okay? It turns out that while you can say that merge sort is always big O n log n, that is the time required to execute merge sort, you can't quite say the same thing for quicksort. Quicksort, actually, my implementation of quicksort is usually, and I would say almost always, significantly, or at least a little bit faster than merge sort. Okay? Most of the time, quicksort executes in an amount of time that is also big O n log n. However, while we can say that that's true of quicksort usually and on average, there are some bad cases when quicksort takes a very long time to execute. Okay? Well, why is it? What is it that slows down quicksort? We'll get back to that question of what it is that sometimes, very, very infrequently, and only in very unlucky cases, what it is that causes sort to execute much slower than it ordinarily does. But right now, let me just assert that in the worst case, when we're unlucky, the only thing we can say is that quicksort's time is only big O of n squared. All right, in other words, the same kind of deal that we have with bubble sort, selection sort, and insertion sort. The time required to execute quicksort, in the worst case, is big O n squared. All right? Now, it may not have hit you yet, but think about this. When n is big, n squared is a lot bigger than n times log n, right? Because if n is big, n is going to be a larger than the base 2 logarithm of n. If that doesn't hit you on a gut level, you really need to think about logarithms. It turns out that if n is a billion, 1 billion, the base 2 logarithm of that is approximately 30, right? So a billion is much, much bigger than 30, all right? And then if you multiply by n, you have that n squared is much, much bigger than n times log n, okay? So it's a bad thing if quicksort is taking an amount of time that's approximately a constant times n squared, when usually it'll take amount of time that is approximately n times constant times n log n. Okay. One thing that we're obscuring here with the big O notation is these constant factors, because you might argue that, okay, well, a constant times n squared versus some other constant times n log n, well, it really does matter what the constants are. And potentially that is true. If the constants are very big, they would have an important impact. But the constants actually that are involved in these things are not particularly large. Okay, so when we say that merge sort and quicksort, at least quicksort on average, execute an amount of time that's approximately a constant times n log n, versus the fact that bubble sort, selection sort, and insertion sort execute an amount of time that's approximately a constant times n squared, okay? Well, those constants are reasonable numbers, and it really is a big deal that we're saying that merge sort and quicksort are, executing at a time that's approximately a constant times log n, versus the others that are executing a time that's approximately a constant times n squared. I really, really, really want you to download the sorting code, as I've been mentioning in the past, so that you can look at and experience this for yourself. We'll get back to that, but you really should be able to see that merge sort and quicksort go much, much faster than bubble sort, selection sort, and insertion sort. So why don't you do this? Download either the Java code or the C++ sorting code and run the following experiment. First, make sure that display is turned on. You'll see comment at the top of the code. It's a little different for C++ versus Java, but you want to have the display turned on for this first exercise. Okay, and then also make sure that n, which is the n in the program, is what we were calling size in some of the code. So the n is actually a global value here that will specify the size of the array of numbers that's used. Okay, the program is going to generate an array filled with random numbers between 0 and 100. Okay? begin with n set equal to 100. Okay, so when this program runs, it'll generate an array of size 100 of random numbers, and it will invoke each of the sorting algorithms we've discussed in turn to sort a copy of that array. Okay, and the execution time for each of the sorting algorithms will be determined and displayed, right? Now, because you have the display business turned on, it'll actually show you the arrays, show you the original array before sorting, and it will show you the result of each of the sorting algorithms actually sorting the array. Okay, if you look at the times involved for sorting 100 numbers, you might not be incredibly impressed. Maybe a little impressed, but not so impressed. So the next thing to do is this: turn off the display feature so that the program will not display the resulting arrays, and set n to something pretty substantial. You might try 10,000 for n, okay? If you set n too big, your computer might be too slow to, in a reasonable amount of time, do the sorting. So if you feel like your program is getting hung up, then somehow interrupt it and set the value of n to something smaller and start over. Okay, but chances are n equal to 10,000 is likely to work for you. Okay, so that will randomly generate an array of 10,000 doubles, and then it will call each of the sorting algorithms in turn to sort a copy of that array, and it will measure the time required, the time involved in doing each of those sorts. Do that. So if you do that, I think you're going to be quite impressed. I think you're going to see that Quicksort is the clear winner, that Mergesort is not too far behind that, and that the other three more basic sorting methods take far, far, far longer to sort. Okay? If you want to, you can try other values of n, maybe go up to 50,000 or 100,000. Okay, the one thing that's actually missing from these slides, I was going to talk about what it is that can make Quicksort perform poorly. In very unlucky cases, Quicksort will go slowly and will go basically as slow as bubble sort and the other more basic sorting methods. And the reason for that is pretty easy to understand. Remember that Quicksort works in such a way that when it splits a subarray into two smaller subarrays, it can't be guaranteed that those two subarrays are approximately the same size. With Mergesort, the two subarrays are going to be approximately the same size, but we can't be assured of that happening with Quicksort. So if we're very, very, very lucky, then over and over and over again at each level of recursion, we get these bad splits where we take a subarray and split it into two subarrays, and because we're unlucky, one of those two subarrays is almost the original subarray, and the other one maybe just consists of one or two elements. Okay, it's very small. Okay, so if that sort of unlucky thing happens repeatedly, then instead of having number of levels of recursion that is equal to the logarithm of n, you'll end up with a number of level of recursion that's actually approximately equal to n. Okay? It's not important to get terribly worked up about this issue right now, but really is that possibility of having bad splits that can screw up quicksort. So I just want you to have a realization of that, a basic appreciation of it without worrying too much about it. All right? I forgot to even include a bullet here, so you're not really responsible for it. Okay? All right. When you're ready and you feel you're prepared as usual, then go and take the self-quiz for part B of the time complexity analysis lecture.